In the Atlantic by May 1944, anti-submarine warfare is governed less by contact probability than by energy accounting. A Type IXC submarine enters patrol with approximately 11,000 ampere-hours of usable battery capacity, a pressure hull rated to roughly 230 meters, and compressed air reservoirs charged to approximately 200 bar. None of these values are theoretical. Each is a finite ceiling. Each defines how many minutes the boat can maneuver, how deep it can dive without structural deformation, and how many times it can correct trim before control degrades. The system does not fail dramatically. It fails by subtraction. U-505 departs on patrol already carrying accumulated stress. Repeated depth charge exposure during earlier operations has not ruptured the pressure hull, but it has altered tolerances. Valve seats no longer seal symmetrically. Minor deformation increases leakage rates under pressure. At 150 meters, a leak measured in milliliters per second behaves as a nuisance. At 180 meters, the same leak becomes kilograms per minute. The technical limiter is pressure-dependent ingress rate because pumping capacity remains fixed while hydrostatic pressure rises linearly with depth. On June 4, 1944, Task Group 22.3 operates west of Cape Verde under hunter-killer doctrine rather than convoy escort doctrine. USS Guadalcanal CV-60 coordinates destroyer escorts including USS Chatelaine D-149 and USS Pillsbury D-133. The group's operational constraint is contact continuity. ASTIC sonar aboard Chatelaine operates effectively within approximately 1,200 meters under favorable conditions, but a thermocline at roughly 60 meters refracts sound and intermittently degrades bearing stability. The limiter is sound propagation geometry, because loss of contact for more than 30 to 40 seconds resets attack geometry and forces reacquisition. Initial contact is established and held. U-505 dives below the thermocline, oscillating between 70 meters and 170 meters to exploit refraction layers. Each depth change requires trim correction. Each correction consumes compressed air and electrical power. At 4 knots submerged speed, propulsion draws approximately 300 amperes. At 6 knots, draw exceeds 600 amperes, reducing endurance to less than 6 hours. The technical constraint is discharge rate versus remaining capacity, because high-speed evasion consumes energy faster than it can be replaced under pursuit conditions. USS Chatelaine closes to Hedgehog launch distance. Hedgehog projectiles travel forward approximately 230 meters and sink at roughly 7 meters per second. From firing to potential contact, time of fall is approximately 30 seconds. Any submarine course change during that interval shifts the impact pattern enough to negate a hit. To avoid this, U-505 alters depth and bearing repeatedly. Each maneuver increases hydrodynamic drag, raising electrical load and internal noise. Noise above baseline increases sonar detection persistence. The limiter is acoustic feedback. Evasion maneuvers increase detectability, which forces continued evasion. Depth charges follow. Detonations at set depths near 150 meters generate pressure impulses exceeding several hundred psi at close range. These impulses do not need to breach the hull. They deform battery plates, crack insulation, and jar electrical panels. Seawater intrusion into lead-acid batteries produces chlorine gas within seconds. Compartments must be isolated. Isolating one battery group removes approximately 50% of available capacity instantly. The technical constraint becomes remaining kilowatt hours because endurance is now mathematically insufficient for prolonged submergence. Atmospheric conditions degrade in parallel. CO2 concentration rises above 2% within hours of sustained submergence. Above 3%, cognitive performance drops measurably. Fine motor control deteriorates. Scrubber chemicals absorb CO2 at a finite rate and saturate. Regeneration is impossible under combat conditions. The limiter is crew functional time, because below certain thresholds, procedural accuracy collapses before mechanical systems fail. Flooding remains controlled but cumulative. A leak rate of 3 to 5 liters per minute adds more than 300 kilograms of water per hour. That mass shifts longitudinal trim by degrees rather than fractions. Each trim correction consumes compressed air. Reservoir pressure falls from approximately 200 bar toward 140 bar. Below that level, ballast blows become incomplete and asymmetric. The technical constraint is minimum effective air pressure, because without it, surfacing becomes uncontrolled. U-505 surfaces abruptly. The ascent is forced, not tactical. Surface speed peaks at approximately 10 to 12 knots due to propulsion impairment and drag from compromised fittings. Destroyer escorts maintain speeds above 20 knots. Escape geometry collapses within minutes. The limiter is surface speed differential, which eliminates maneuver options regardless of intent. Abandonment follows standard doctrine under abnormal timing. Scuttling charges are placed, but not fully synchronized. Seacocks are opened but not verified. Flooding begins but does not reach reserve buoyancy threshold before the crew departs. The submarine remains afloat. The constraint is flooding progression time, measured in tens of minutes, not hours, but sufficient to allow intervention. Boarding teams from USS Pillsbury move immediately. Each hatch passage restricts movement to single personnel. Vertical ladders slow extraction under load. Rising water reduces mobility in stages. Ankle height, knee height, waist height. Priority is given to radio room and control spaces. The limiter is extraction time per compartment because each minute increases water mass and reduces access. Recovered materials include operational codebooks, short signal manuals, and traffic indicators current for June 1944. Short signal tables compress reports into transmissions lasting seconds. Once captured, they allow reconstruction of intent for minimal intercepts. The technical constraint governing exploitation is processing latency, because intelligence must be analyzed and disseminated within hours to retain value before key rotation. To preserve that window, the capture itself must remain unknown. U-505 is reported as sunk. Survivors are isolated. Radio silence is enforced. The submarine is towed at approximately 7 to 8 knots to limit towline tension and hull stress. Excess speed risks oscillatory loads sufficient to snap lines or tear fittings. The limiter is mechanical load tolerance under tow, because loss of the hull risks exposure of the capture itself. As intelligence integration begins, ASW operations shift subtly. Hunter-killer groups reposition patrol boxes by 20 to 50 nautical miles based on inferred patrol logic. Aircraft patrol altitudes adjust between 1,500 and 3,000 meters to optimize radar horizon against fuel consumption. Recharge windows are predicted within margins of 30 to 45 minutes based on battery endurance models. The constraint enabling this is predictive accuracy, because narrowing temporal uncertainty reduces search volume exponentially. German command receives no anomaly signal. U-505 is logged as lost. Encryption procedures remain unchanged. Patrol doctrine persists. The limiter is organizational feedback delay, because without evidence of compromise, corrective action does not trigger. Allied advantage compounds silently. From this point, the Atlantic becomes a closed energy system for submarines. Each patrol consumes more kilowatt-hours per contact avoided. Each avoided contact shortens the next recharge window. Each shortened window increases detection probability. The submarine does not lose because it is weak, but because its margins are consumed faster than doctrine can replace them. What U-505 provides is confirmation of those margins in real numbers, converting uncertainty into schedule and schedule into pressure. As exploitation matures, Allied ASW planning shifts from contact-centric to schedule-centric operations. Battery endurance models for Type IXC boats are refined using recovered logs and technical manuals. A boat operating at 3 knots draws approximately 180 amperes. Hotel load adds another 40 to 60 amperes, depending on lighting and pump usage. At that rate, a battery bank depleted to 35% requires at least 5.5 to 6.5 hours of uninterrupted surface, charging to restore to 80% using both diesels at nominal output. Any interruption longer than 90 seconds forces engine shutdown and restart, adding thermal and acoustic signatures and reducing net gain. The technical limiter is uninterrupted charge duration because partial cycles do not accumulate, they decay. Air patrol tasking begins to exploit this arithmetic. Radar-equipped aircraft schedule search legs to intersect predicted recharge windows rather than patrol boxes. A radar sweep at 2,000 meters altitude extends the horizon to approximately 95 kilometers. At cruising speed, an aircraft covers that arc in minutes. Detection of a snorkel mast or conning tower produces a response window measured in 180 to 240 seconds before the submarine can dive below 30 meters. The limiter is dive initiation time, because a crash dive requires valve sequencing and ballast response that cannot be accelerated beyond mechanical limits. Crash dives themselves impose cost. A dive from surface to 50 meters at emergency rate takes approximately 35 to 45 seconds and requires rapid ballast flooding. The sudden inrush stresses valves and hull fittings already compromised by prior shock loading. At depth, rapid trim correction consumes compressed air at rates exceeding normal patrol consumption by multiples. The constraint is emergency maneuver penalty, because each forced dive trades immediate concealment for accelerated depletion of air and electrical reserves. Hunter-killer surface units exploit this depletion by maintaining contact persistence rather than immediate attack. Sonar contact held for 10 to 15 minutes forces the submarine to remain at depth, preventing recharge and increasing CO2 concentration. CO2 rises at approximately 0.5% per hour under low ventilation. After 6 hours, levels approach thresholds where sustained vigilance is impossible. The technical limiter is human endurance under degraded atmosphere, because mechanical systems may still function while crew effectiveness collapses. Damage accumulation continues even without direct hits. Propeller shaft alignment drifts by fractions of a degree under repeated shock. That misalignment increases vibration, raising acoustic signature by several decibels. A 3 to 5 decibel increase can extend sonar detection range by hundreds of meters under favorable conditions. The constraint is acoustic margin, because small increases in noise disproportionately expand the volume in which a submarine can be held. Intelligence derived from U-505 tightens these margins further. Traffic indicators reveal reporting intervals accurate to within minutes. Weather keys allow analysts to correlate sea state with likely operational decisions, such as when commanders choose to recharge or remain submerged. Combined, these inputs allow Allied planners to assign assets with timing precision measured in quarter hours. The limiter is temporal resolution, because higher resolution collapses uncertainty faster than additional force would. German countermeasures attempt to adapt within existing hardware limits. Transmission lengths are reduced. Reporting frequency is altered. Patrol routes are shifted. None of these measures alter the underlying arithmetic of energy and air. Reduced transmissions do not reduce the need to recharge. Altered routes do not change patrol duration requirements. The constraint remains fixed physical capacity, because doctrine cannot create kilowatt hours or compressed air where none exist. As summer progresses, loss patterns change subtly. Boats are lost earlier in patrol cycles. Survivors report fewer attack attempts before forced withdrawal or destruction. Average patrol duration drops by days. Each day removed represents a lost opportunity to amortize the cost of deployment. The technical limiter is cost-to-effect ratio, because a submarine that spends more time evading than attacking fails economically even before it fails tactically. The Atlantic thus enters a phase where predictability replaces surprise. A submarine's movement is inferred not from sighting but from necessity. It must recharge. It must ventilate. It must transmit. Each requirement has a minimum time and depth envelope. Those envelopes overlap with detection systems optimized to exploit them. The constraint is requirement convergence, because when multiple necessities align temporally, concealment collapses. U-505's capture reinforces this convergence by validating assumptions. Models built on incomplete data become anchored to real measurements. Error bars shrink. Planning confidence increases. ASW assets are used more efficiently, allowing coverage density to increase without additional ships or aircraft. Efficiency itself becomes pressure. Pressure compresses margins. Margins define survival. By late 1944, the submarine's operational identity changes. It is no longer a platform that chooses when to engage. It is a platform that responds to imposed schedules. Engagement becomes incidental. Survival becomes primary. In that state, any additional constraint, whether mechanical fault, delayed recharge, can push the system past recovery thresholds. The technical anchor is margin exhaustion, because once margins are consumed, Outcomes become deterministic rather than probabilistic. The capture of U-505 does not introduce a new weapon into this environment. It removes uncertainty from existing ones. In an industrial war, removal of uncertainty is often more decisive than the introduction of force. When minutes, meters, amperes, and decibels are known rather than guessed, planning shifts from search to interception. At that point, the submarine's remaining advantage, concealment, exists only within margins too thin to absorb repeated cycles of pressure. By autumn 1944, the Atlantic engagement cycle stabilizes into a repeatable sequence governed by fixed physical limits. A Type IXC departing on patrol carries enough fuel for weeks, but only enough electrical energy for days under pressure. Every contact avoidance maneuver converts diesel endurance into electrical debt. That debt must be repaid at the surface. Repayment requires exposure. Exposure duration becomes the decisive variable. Recharge behavior becomes increasingly constrained. To avoid radar detection, diesel output is throttled below optimal charge rate. At reduced output, battery recharge efficiency drops sharply. A recharge session that should restore 20% capacity in 60 minutes now restores less than 10%. The constraint is charge rate versus exposure tolerance, because extending recharge time increases detection probability faster than it restores endurance. Allied planners integrate these constraints into patrol scheduling. Aircraft sorties are timed to overlap statistically unavoidable recharge windows. A submarine depleted to 30% battery capacity cannot delay recharge beyond approximately 10 to 12 hours without risking immobilization. This creates a predictable temporal band. Patrol aircraft crossing that band at intervals of 90 minutes ensure repeated interruption. The technical limiter is minimum viable battery threshold because once crossed, the submarine loses the ability to maneuver silently. Repeated forced dives accelerate mechanical degradation. Rapid flooding of ballast tanks during crash dives induces transient stresses in hull fittings and piping. Over time, these stresses increase leakage probability. Leakage increases pumping demand. Pumping increases electrical load. The constraint is cumulative stress amplification, because each emergency response degrades future response capacity. Sonar doctrine adapts to exploit this degradation. Escorts reduce attack intensity once damage indicators appear, focusing instead on maintaining contact. Continuous sonar tracking denies the submarine recovery time, even without weapon release. Holding contact for 20 to 30 minutes prevents battery conservation and forces the boat deeper into energy deficit. The limiter is recovery denial, because preventing recharge is more decisive than inflicting damage. Crew performance continues to decline under these conditions. At CO2 concentrations sustained above 2.5% for multiple hours, error rates increase measurably. Valve misalignment, delayed responses, and incomplete procedures become more frequent. These errors compound mechanical problems. The technical constraint is human error amplification, because small mistakes under degraded conditions produce outsized system effects. Intelligence exploitation from U-505 further refines this cycle. Traffic analysis reveals average reporting intervals measured in hours. Deviations from those intervals indicate distress, pursuit, or enforced radio silence. Allied planners use absence of signal as signal. Assets are redirected based on silence duration exceeding predicted endurance windows. The limiter is inference confidence, because when silence itself becomes data, concealment loses meaning. German command attempts to counter by extending patrol areas and staggering transmissions. These measures increase transit time and fuel consumption without increasing operational effect. Longer transits reduce on-station time. Reduced on-station time reduces attack opportunity. The constraint is transit overhead, because time spent moving without attacking consumes endurance without producing results. As winter approaches, environmental factors add pressure. Rougher seas increase radar clutter, but also increase mast vibration during snorkel use, raising acoustic signature. Poor weather delays recharge, but does not eliminate need. The technical limiter is weather interaction, because conditions that reduce detection also reduce recharge efficiency, preserving the overall pressure balance. By late 1944, the submarine's decision space collapses into narrow corridors. Choices are no longer strategic, but reactive. Dive now or recharge later. maneuver or conserve, transmit or remain blind. Each choice trades one finite resource for another. The system no longer allows accumulation of advantage. It only allows delay of failure. The capture of U-505 feeds this environment indirectly but persistently. It validates endurance models. It confirms procedural assumptions. It narrows error margins. With narrower margins, Allied forces require fewer assets to achieve the same level of pressure. Asset efficiency rises. Pressure density increases. The constraint is efficiency scaling, because improved efficiency multiplies effect without visible escalation. At this stage, the Atlantic ceases to be an arena of encounters and becomes an accounting problem. Each patrol is an equation balancing kilowatt-hours, compressed air bar, CO2 percentage, and minutes of exposure. The side that forces the other to solve that equation more often and under worse initial conditions determines the outcome. The submarine remains dangerous, but danger no longer equates to survivability. By early 1945, the Atlantic anti-submarine system functions as a closed-loop pressure mechanism. Submarines no longer encounter escorts randomly. They encounter them as a consequence of resource depletion. A Type IXC operating under continuous ASW pressure averages 2 to 3 force dives per 24-hour cycle. Each force dive consumes approximately 5 to 7% of remaining battery capacity due to high-speed descent, trim correction, and recovery to silent running. Over 48 hours, this alone removes up to 30% of usable electrical reserve without a single weapon detonation. Recharge attempts under these conditions become fragmented. Instead of a continuous 6 to 8 hour surface interval, boats achieve multiple interrupted recharge bursts lasting 15 to 40 minutes. At reduced diesel output, each burst restores only 3 to 6% capacity. Net daily balance becomes negative. The technical limiter is recharge fragmentation, because cumulative gain cannot exceed cumulative loss once interruptions exceed a critical frequency. Escort behavior adapts to enforce this imbalance. Destroyer escorts rotate contact, holding duties to maintain sonar pressure without exhausting crews or fuel reserves. A submarine held at depth for 25 to 30 minutes is denied both recharge and atmospheric recovery. CO2 concentration rises incrementally with each cycle. After 3 to 4 such cycles, internal atmosphere approaches thresholds where sustained alertness is no longer possible. The constraint is atmospheric recovery time because it exceeds the denial interval imposed by escorts. Mechanical reliability degrades predictably. Pumps run longer to counter leakage. Motors operate hotter due to sustained load. Electrical insulation weakens. A motor drawing an additional 20 to 30 amperes due to inefficiency accelerates discharge noticeably over hours. The technical anchor is efficiency loss rate because small degradations compound faster than maintenance cycles can compensate. Intelligence exploitation tightens spatial confinement further. Analysis of U-boat traffic patterns reveals average transit speeds and patrol leg durations. Deviations from expected timelines indicate pursuit or evasion. Allied planners allocate air patrols to intersect these deviations. A submarine delayed by 2 to 3 hours on a patrol leg is statistically more likely to attempt recharge within a defined radius. The limiter is scheduled deviation detectability because timing anomalies become targeting cues. German adaptations increasingly trade stealth for endurance. Snorkel use increases, but snorkel operation constrains depth to less than 20 meters and limits speed to approximately 4 knots. Mast vibration increases acoustic output. Exhaust plumes and mast heads become radar visible under favorable conditions. The constraint is vertical maneuver denial because the submarine forfeits access to deep water to regain limited electrical endurance. Winter sea states introduce additional penalties. High seas increase mast stress during snorkel use, raising failure probability. Diesel intakes ingest spray, forcing shutdowns. Each shutdown interrupts charging and requires restart sequences that emit distinct acoustic and thermal signatures. The technical limiter is weather-induced interruption frequency because rough seas degrade recharge efficiency more than they degrade detection capability. As patrol cycles shorten, logistical pressure emerges. Boats return with unused torpedoes. Engagements are aborted before firing solutions mature. Reload cycles are interrupted. The constraint is engagement setup time because a successful attack requires uninterrupted minutes at periscope depth that no longer exist consistently within the detection envelope. By this stage, Allied forces no longer require continuous contact to achieve effect. Intermittent pressure suffices. A single air contact or sonar hold resets the submarine's recovery clock. The system punishes attempts at stabilization. The technical anchor is recovery reset because denial of stabilization is equivalent to damage over time. The capture of U-505 contributes to this condition by confirming assumptions rather than introducing surprises. Its logs validate endurance estimates. Its procedures confirm timing models. Its equipment verifies noise and recharge characteristics. With validation, planners act with higher confidence. Confidence reduces caution. Reduced caution increases pressure density. The constraint is confidence amplification, because validated models are applied more aggressively than theoretical ones. At this point, survivability becomes statistical rather than tactical. Individual skill still matters, but it operates inside margins too thin to absorb repeated stress cycles. Boats are lost not because of singular mistakes, but because accumulated deficits cross irreversible thresholds. Electrical reserve drops below maneuver minimums. Air pressure falls below control requirements. Crew performance degrades below procedural reliability. These thresholds are crossed quietly. The Atlantic thus resolves not through decisive engagements, but through convergence. Energy limits, atmospheric limits, acoustic limits, and timing limits align. Once aligned, they remove choice. The submarine still moves, still dives, still surfaces, but each action is constrained by numbers that no longer favor recovery. The system does not need to destroy every boat. It only needs to ensure that recovery becomes mathematically improbable before patrol objectives can be fulfilled. By the beginning of 1945, the Atlantic operating environment enforces a convergence of limits that no longer require continuous contact to remain effective. A Type IXC attempting to recover endurance after 48 hours of pressure must restore at least 25 to 30% battery capacity to regain tactical mobility. At reduced diesel output, to limit acoustic and thermal signature. Restoring that margin requires a minimum uninterrupted surface interval of approximately 3.5 to 4.0 hours. In practice, average uninterrupted intervals fall below 40 minutes. The technical limiter is minimum recovery block length, because recovery below that threshold never reaches functional sufficiency. Air patrol density now overlaps these recovery requirements with deliberate timing. Patrol aircraft cycle through predicted recharge bands every 60 to 90 minutes. Even a single radar contact forces a crash dive, resetting the recovery clock. A crash dive consumes approximately 4 to 6% battery capacity within the first 5 minutes due to high-speed descent and trim stabilization. The constraint is recovery negation, because one interruption erases the net gain of multiple short recharge attempts. Surface escorts exploit the same arithmetic. Once sonar contact is established, escorts do not need to destroy the submarine immediately. Holding contact for 15 to 20 minutes denies both recharge and atmospheric normalization. CO2 concentration, already elevated, continues to rise at approximately 0.4 to 0.6% per hour under low ventilation. After multiple cycles, internal atmosphere approaches 3% CO2, a level at which sustained decision-making accuracy degrades measurably. The limiter is atmospheric normalization time because it exceeds the denial interval imposed by coordinated ASW pressure. Mechanical systems degrade under this regime in predictable ways. Cooling efficiency declines as pumps operate continuously to counter leakage and heat buildup. Motor windings experience thermal stress. A temperature increase of even 10 to 15 degrees Celsius above nominal raises electrical resistance, increasing current draw for the same shaft output. Over hours, this additional draw shortens endurance by measurable margins. The technical anchor is thermal inefficiency accumulation because heat converts electrical capacity into waste faster than design tolerances allow. Intelligence exploitation continues to sharpen timing. From recovered U-505 traffic materials, analysts derive average reporting intervals and variance bands. When a boat fails to transmit within its expected window, probability of pursuit or enforced silence rises sharply. Assets are redirected based on silence duration exceeding modeled endurance margins. The limiter is silence interpretation threshold, because absence of signal becomes an actionable data point rather than a gap. German countermeasures increasingly exchange concealment for endurance. Snorkel use expands, but snorkel operation constrains depth to approximately 15 to 20 meters and limits speed to about 4 knots. Mast vibration adds broadband noise. Exhaust flow introduces thermal and radar signatures. Under moderate sea states, snorkel head failure rates increase due to bending stress and spray ingestion. The constraint is vertical maneuver confinement, because regaining electrical endurance requires surrendering depth-based concealment. Weather compounds these limits rather than relieving them. High seas disrupt visual detection, but increase acoustic noise from mast and hull interaction. Diesel intakes ingest spray, forcing shutdowns. Each shutdown interrupts charging and requires restart sequences lasting several minutes, during which no net energy is gained. The technical limiter is weather-induced charge interruption frequency, because rough conditions degrade recovery efficiency faster than they degrade detection capability. Operational outcomes shift accordingly. Boats return with torpedoes unused. Engagements are aborted before firing solutions mature. Periscope exposure time required for accurate targeting exceeds safe windows by tens of seconds. Each aborted setup represents not just a missed attack, but an additional cycle of forced maneuvering and energy loss. The constraint is setup duration mismatch because offensive action no longer fits within survivable exposure envelopes. At this stage, ASW pressure functions statistically. A single air contact or sonar hold does not destroy the submarine, but increases the probability that the next recovery attempt will fail. Failure cascades. Battery reserve falls below maneuver minimums. Compressed air pressure drops below reliable ballast control thresholds. Crew performance degrades below procedural reliability. These thresholds are crossed quietly, without a single decisive blow. The technical anchor is cascading threshold failure, because once crossed, recovery becomes mathematically improbable. The capture of U-505 integrates into this system by validating the numbers that govern it. Endurance tables align with real performance. Noise estimates align with sonar results. Recharge models align with operational behavior. With validation, planners compress safety margins further. Reduced margins increase pressure density. Increased pressure density accelerates threshold crossing. The constraint is model confidence amplification, because validated models are applied with greater aggressiveness than theoretical ones. By this point, the Atlantic no longer offers space for adaptation through doctrine alone. Hardware limits dominate outcomes. Energy, air, sound, and time define survivability more rigidly than tactics. Submarines still move, still dive, still surface, but each action consumes a resource faster than it can be replaced. The environment does not need to be sealed. It only needs to ensure that replacement rates remain below consumption rates for long enough. What remains is not a contest of initiative, but a process of exhaustion measured in minutes, meters, amperes, and decibels. Once those measures align against recovery, the outcome is no longer uncertain. It is scheduled. The historical scale of U-505 becomes visible only when measured against rates rather than events. By mid-1945, Allied anti-submarine warfare has converged on a regime where survivability is governed by replacement speed versus consumption speed. For a Type IXC, electrical replacement requires uninterrupted surface time measured in hours. Consumption under pressure occurs in minutes. That asymmetry defines the outcome. A patrol that loses 5% battery capacity per forced dive and gains 4% per interrupted recharge cannot stabilize, regardless of crew discipline or tactical ingenuity. The mathematics do not permit equilibrium. What U-505 adds to this system is not novelty but certainty. Before June 1944, planners operate with tolerances. After June 1944, tolerances shrink. Battery tables align with observed discharge curves. Trim corrections align with compressed air pressure decay. Sonar contact persistence aligns with measured noise increases of 3 to 5 decibels after repeated shock loading. With alignment, planning horizons shorten. Aircraft sorties are timed to intersect recharge windows within 30 to 45 minutes. Surface units hold contact for 15 to 20 minutes to deny atmospheric recovery, known to require longer than the denial interval. Each parameter tightens until coincidence becomes routine. At the operational level, this produces a shift from destruction to scheduling. Escorts no longer need to expend ammunition to achieve effect. A held contact denies recharge. A denied recharge forces surfacing. A surfaced boat is detected within 180 to 240 seconds at radar ranges, defined by altitude and sea state. A crash dive consumes 4 to 6% capacity within the first 300 seconds. The cycle repeats. The limiting variable is minimum viable reserve. Once reserve falls below maneuver thresholds, options collapse without further enemy action. At the doctrinal level, the war demonstrates that concealment is conditional, not inherent. A submarine's invisibility exists only while energy, air, and noise budgets remain within bounds. When those budgets are known and modeled, concealment becomes predictable. Prediction reduces search volume. Reduced search volume increases contact probability without increasing force size. Force efficiency rises. Pressure density increases. The ocean does not shrink, the safe corridors do. At the strategic level, U-505 marks a transition in information warfare. Signals intelligence had long existed, but capture validates inference. When absence of transmission becomes data, silence loses protective value. When patrol timing can be inferred from endurance arithmetic, movement becomes legible without sighting. This does not require perfect decryption. It requires confidence that estimates are correct within minutes and miles. After validation, planners act earlier, closer, and longer. German command's delay in recognizing compromise is not a failure of vigilance, but a consequence of attrition masking. Losses accumulate within expected bands until thresholds are crossed. By the time patterns separate from noise, corrective measures would require disruptive changes, new keys, new doctrine, new hardware, that cannot be fielded at the speed demanded by the pressure cycle. Organizational latency becomes a physical constraint. The broader lesson is industrial. Systems defeat platforms by exhausting margins. In the Atlantic, victory is achieved when recovery rates are forced permanently below consumption rates. Once that condition holds, outcomes are scheduled rather than contested. U-505 does not end the submarine war. It shortens the distance between survivable patrols and inevitable exhaustion by tightening the numbers that govern each cycle. In that light, the capture is neither anomaly nor trophy. It is a calibration event. It converts estimates into constraints and constraints into schedules. After calibration, the Atlantic becomes an accounting problem solved in amperes, bar, decibels, meters, and minutes. When accounting replaces uncertainty, concealment ceases to be sanctuary. The submarine remains capable, but capability without margin is transient. What decides the war is not the moment of contact, but the rate at which the system denies recovery until recovery is no longer possible.